Thank you for hanging in there for a long, exciting day. I think I actually made fewer slides than I technically could have, so maybe I'll bring us all to a happy close sooner than later. I'd like to tell you a little bit about direct mapping of dark matter in the galaxy. And as we heard in the last talk, if you're looking for dark matter, we don't for direct detection of dark matter, whether you're looking for heavy WIMP-like particles or light scalars, to interpret any results you get, you need to know what the dark matter density in the local neighborhood is. And we have estimates of that, but it would be nice to have a direct measure of what the local dark matter density is. And I'd like to tell you, and in addition to being able to use it to reference direct detection experiments, it can also help us understand the structure of the Milky Way a little bit better and interpret results that are coming out of Gaia. And so I would today like to tell you a couple different ideas we've had about how to perform these measurements. First, the 2-minute introduction to dark matter. You've almost certainly all seen this picture before. This is the galactic rotation curve. One of the earliest ways that people said, if you just calculate the gravitational force from matter we can see, that is from stars, we would predict some Keplerian, kind of almost solar system-like motions for the stars orbiting the galaxy. But in fact, if we go measure the velocities of stars orbiting the galaxy and also measure the orbital velocities of the hydrogen gas that's in the outskirts of the galaxy, we see a flat line. And that was one of the earliest indications that something was wrong with the simplest picture. I'd like to pause for a moment at this point and say the sun is about 8 kiloparsecs, and I'm going to use a whole weird mishmash of units, and you have my humblest apologies, and start throwing tomatoes at me and asking for translations to other units if you want. But the sun is about here. And so when you're... Thank you. I'm bellowing so much that I can't even tell I don't have the mic on. Let's try again. Oh yeah, now I can hear it's on. And so while you might say that, hey, the Keplerian prediction doesn't do so badly as far out into the galaxy as we are, that actually, if you have skepticisms about dark matter, and it's hard not to have, given the universe we live in, it's hard not to be skeptical of kind of everything, then this makes you even more want to know, to actually measure the gravitational potential and extract the dark matter component from it. And so how do we do that today? Here's a really complicated, ugly picture of showing forward modeling of the galactic rotation curves. But in fact, what's typically done is to look at the distribution of stellar velocities and using the virial theorem and assuming equilibrium and all kinds of things, going from a distribution of velocities to a local acceleration. One of the things that we've learned from Gaia, and we kind of knew this before, but if anybody had any doubts, Gaia has certainly shown us, is that dwarf galaxies have collided with the Milky Way so recently that the stars that have come into the Milky Way from these dwarf galaxies have not had time to complete one full orbit around the center of the galaxy. And so assuming equilibrium is almost certainly a mistake. Now, the people who do these calculations are very smart people who have worked very hard and know an enormous amount. And so they're probably mostly right. And so maybe a safer way to say what I'm trying to say here is that there's a set of systematics associated with the current methods of trying to extract the gravitational potential in the galaxy. And there will be a set of systematics associated with what I'm about to show you, and they'll be extremely different. And so by being able to compare and contrast current static snapshot pictures of the galaxy used to extract the gravitational potential from more dynamical methods that I'm about to tell you about can help us understand the systematic issues in these very important measurements. So the basic idea that I would like to tell you about is to use the techniques of precision radial velocity measurements, which have been used for the past 20, 25 years to look for exoplanets, to measure the gravitational potential. And what do we do when we look for exoplanets using the radial velocity technique? We measure a Doppler shift. We measure a Doppler shift, and we watch as a star wobbles as a planet orbits it. Well, let's just take some star and measure its velocity and come back in a decade and measure its velocity again. And from the difference, we know the acceleration. And that is the total gravitational acceleration on a star. These numbers turn out to be somewhat challenging. And the whole rest of my talk is all about this is a challenging thing to do. If you work out some numbers, again, we're 8 kiloparsecs from the center of the galaxy. We're orbiting the center of the galaxy with a velocity of about 220 kilometers a second. That corresponds to an acceleration of 10 to the minus 8 centimeters per second squared. No problem. If we convert this to units that exoplanet astronomers are used to, which is to say centimeters a second, the acceleration of the sun as it orbits the galaxy is 5 centimeters a second a decade. And so all we have to do is measure the radial velocity of stars in the galactic in the solar neighborhood with a 5 to 10 centimeter a second precision repeatedly for a decade. So I put this in here. We wrote this all up in a paper. After a little bit of battle, it was accepted. So the first 2/3 of what I'm going to tell you here today is all the work of the graduate student Akash Ravi, who's defending his PhD next month. And he did yeoman's work, both working out all the details here and getting it through the publication process. But the key thing is that we believe that that we can do 10 to the minus 8 centimeter per second squared acceleration measurements. And if we have an ensemble of about 300 stars, about 1,000 stars in a few kiloparsec volume in the local solar neighborhood, we can determine the dark matter content. And so once again, the basic idea is you pick some stars that are closer to the center of the galaxy than we are, and you measure their radial velocities, and then you pick some stars a little further from the galactic center than we are, and we measure their radial velocities, and then we wait 10 years and we measure them again, and from that we figure out dark matter. Now, you might say, so if you've been paying attention to exoplanet astronomy, which probably some of you have, but maybe a lot of you haven't, the state of the art right now is about 1 meter per second. And so once again, I'm kind of giving you weird units. I mean, you know what a meter per second is if I'm walking down the street. But in terms of doing measurements on stars, what does this mean? Well, divide by the speed of light. And so this is like a meter per second is a few ppb measurement of Doppler shifts on a star. And the other way to think about it is if I say a meter per second, here a megahertz. At 500 nanometers, a meter per second is about a megahertz. And so to do 10 centimeters a second, we're doing 100 kilohertz optical measurements. And all of you optical clock people are like, how can you possibly do as poorly as 100 kilohertz optical measurements? We are looking at stars that are a long ways away, and we have no systematic controls over anything. But to make life even harder, these stars are 5,000 degrees. And so all the spectral features that we're going to use to look for Doppler shifts are broadened to 5 gigahertz or 10 gigahertz. And so we're trying to do 100 kilohertz we're trying to do 10 to the 5 line splitting. Did I do that right? Yeah, I did that right. 10 to the 5 line splitting on light from stars where every photon is precious and we don't get many photons. But the next generation spectrographs are all promising 10 centimeters per second. And I, in my what you might call night job, I'm looking for exoplanets, and we all promise we're going to find terrestrial exoplanets. And so there's an army of 1,000 of us, or some number like that. 1,000 of us sounds good, trying to hit the 10 centimeter per second level. And so while this is a really challenging problem, we'd better solve it. And when we solve it, we can then go measure dark matter. And so let me say a few more words about some of the challenges of doing 10 centimeter per second astronomy. How I got involved in this was through frequency combs. An important thing, an astrophysical spectrograph is some giant room full of glass and metal. The actual spectrograph is inside a vacuum can here. But if you ask, how stable can some meter scale thing of glass and metal be? Well, in round numbers, the thermal expansion coefficients are 10 to the minus 5 per degree, and maybe I can stabilize to a millidegree. This thing is a couple meters long. Stabilizing it to a millidegree is maybe easier said than done, but we get close. And so that's something like 10 to the minus 8 fractional stability. Times the speed of light again, we're back up at 3 meters per second. And so what you need to do is you need to calibrate. And so you want to inject a bunch of known optical wavelengths into your spectrograph and calibrate it. And what's better than a frequency comb? I could spend 45 minutes talking about using frequency combs to calibrate spectrographs, but I'm going to have one more slide and then be done. We get great stabilities. We get down to 1 centimeter per second calibration of the spectrograph in terms of if you tell me what pixel light from the star is on, I can tell you what its wavelength is. We can do that to a centimeter per second. But now if you look at the point spread function, if I put a monochromatic beam of light into my spectrograph, what do I get out? Well, depending upon, I get this, and depending upon where on the spectrograph, what wavelength the light is, sometimes it's asymmetric that way, and sometimes it's asymmetric that way, and sometimes it's actually pretty symmetric. And if we watch this behavior over time, it changes. And so calibration is not enough. You actually really have to understand what your instrument is doing. And our field is just coming to grips with that right now. I get into long discussions with people who vote for the don't worry, be happy theory. And I push for maybe we should admit that we're precision measurement people and go understand what our instrument actually does. But part of the reason other people say don't worry, be happy is if you thought the instrument was bad, the stars are even worse. Like you'd like to think that the sun is this nice spherical ball of plasma and it's all happy and uniform and everything's wonderful. Of course, if you go look at those cool pictures from the Solar Dynamics Observatory and you see all these flares and you see sunspots and you see hot active regions, stars are a mess. And the one star that we understand, or the one star whose radial velocity we know is the sun. And so I've spent, in trying to understand how to do these measurements, I've spent the last 4 years running a small solar telescope that feeds one of the state-of-the-art spectrographs. And so here you can see up at the top is a couple years of data of solar radial velocities after subtracting off the right answer, of course. And you can see there's about a meter a second worth of noise. And that's not instrument noise. That's not photon noise. That's the sun being miserable. And the sun is about the quietest star there is. And so we've been, and I could talk to you for hours on end about the things we're trying to do to help, everything from looking for complicated spectroscopic signatures of what's going on the sun to machine learning, where you pretend like you don't need to know what's actually happening on the sun. We're trying to, and everything in between, we're trying it. And we're getting it. We're making progress. I believe that before we have the 30-meter telescope that we need to do these dark matter surveys, we will be down to 10 centimeters a second. But it's a bunch of work. For purposes of that paper, we said, okay, we have all these effects. We have the gravitational acceleration acting on stars. Most stars are in binary systems, and so we're doing these simulations. We include the possibility that there are binaries. Most stars have planets orbiting them, so we include those. And this horrible activity, we include that too. And so we do a simulation and look to see what we get. And we want to be at 10 to the minus 8 centimeters per second squared. And we find that if we have about 1,000 stars with a 30-meter telescope that will let us sample a few kiloparsecs, which is farther away than anyone has done exoplanet radial velocity work before, we can do it. However, we basically need to own the 30-meter telescope. So we need the telescopes that have not come online yet and won't come online for their 5 or 6 years. We need a decade of it. So this is a very challenging proposal. And we're busy thinking about, are there ways that we can be more sophisticated in picking and choosing stars and being clever in our analysis to cut the number of stars we need by an order of magnitude so that we only ask for a year of the 30-meter telescope, which we might get to do this measurement. But yeah, so that's where this stands right now. I think it's a great idea, and I think it's going to be an interesting struggle to try and get enough telescope time to both reduce the amount of telescope time we need compared to the naive numbers and convince people that this is worth spending time on. Oh, yeah, and you really need next generation instruments. If I look at old exoplanet data, we're about more than an order of magnitude too noisy, which is exactly what you would expect from what I just told you, that we need 10 centimeters a second, and state of the art right now, or especially a few years ago when this data was taken, is more like 1 meter a second. So what can we do today? And so what I just told you was all published. This is what I was doing yesterday and the day before. So please don't scoop me, because it's probably going to be another month before I have this all written up. But we can do exactly the same thing as I was describing with sun-like stars using the technologies that we used to look for exoplanets. We can instead do with pulsars. Pulsars are these they're very small, highly magnetized stars that give off regular pulses of radio waves. And in fact, you can basically understand the pulses from a pulsar with two numbers, the pulse rate and the first derivative of the pulse rate. And that's all the information there is. And what these guys, Nanograv is the US collaboration, there's a couple other collaborations around the world, are using pulsars to look for long wavelength gravitational waves, to actually see the arrival time, to see in the residuals of the arrival time of pulses from pulsars, to see systematic variation associated with gravitational waves. And so they have spent the last 15 years very carefully observing pulsars. But now, as a pulsar accelerates around the center of the galaxy, its Doppler shift will change, and the pulsar pulse arrival rate will change. And so we can use that same first derivative of the pulsar rate to go try to measure the gravitational potential. And I'm showing here a plot of the spin-down rate of pulsars and the pulsar pulse rate for all the known pulsars. You can go to an Australian website and you can download the data of all the pulsars. And the first thing you'll notice is that the millisecond pulsars, which are all in binary systems, are also the ones that spin down the most slowly. And if we look at the effective acceleration associated with these spin down rates, it's in the 10 to the minus 8 to 10 to the minus 9 centimeters per second squared, which is exactly what we need to be sensitive to the gravitational potential. And however, there are two other things that, that in addition to the acceleration of the pulsar, there are two other things that cause spin down. One is a real live intrinsic spin down of the pulsar. There's a beam of energy coming out of the pulsar, and it's surrounded by diffuse matter, by the remnants of the supernova explosion. And so as that electromagnetic energy sweeps through the ionized, through the plasma of the nebula, it applies a torque back to the neutron star and it spins down. And also, I kept making this slide simpler and simpler because I didn't want to talk about it, but just in case there's any experts in the room, as what we measure with the Doppler shift is the radial velocity, the component of velocity in the direction that the star is. But now, if the star is moving in the plane of the sky, transverse to the radial direction, then the component of the velocity that's the radial velocity will change. And it turns out that for typical velocities of pulsars in the galactic neighborhood, that's also at about the 10 to the minus 9 meters per second squared level. And so you want the real acceleration, but you have to deal with this geometric effect, and you have to deal with the real spin down of the pulsars. And so, in conclusion, what I've done to...
The gravitational spin down, which is what nanograv was looking for.
Yeah. Right, yes, that as well, yes. That's even smaller, though. So what I've done to date is to take all of these components and put them into a simulation, and I find that if I have 50 pulsars, the realistic parameters that come back from this picture, from the distribution of millisecond pulsars, if I have 50 of them, I can do 1 10 to the minus 9 centimeters per second squared, which is good enough to not just see the gravitational potential, but extract dark matter, to resolve the dark matter at the 10% level. So this is super exciting. One problem is that there's only about 10 pulsars right now whose proper motion, whose motion on the plane of the sky is known well enough to apply corrections at this level. And so I'm probably more like at the 3 or 4 times 10 to the minus 9 centimeters per second squared right now. But I think that today we can observe the gravitational potential, and on Gaia's data release 3, when we have more companions to the binary pulsars, when the astrometry for more pulsars is measured, then I think we can be here. And that's like a year from now. year and a half from now. And so I am super excited right now to make the transition from what I've been doing for the past couple of weeks of working in simulation, because I don't want to touch the real data until I know what my analysis scheme is, to actually go apply this with real data. And so I think that we can have a dynamical measure of the gravitational potential today or almost today. And so with that, let me say thank you.
How long will Gaia be around?
I believe that their extended mission has just been approved. Or no, I think they might even be in extended mission now. So probably 3 or 4 more years.
So can you use Gaia as 2 points separated in time to get velocities?
Gaia doesn't get you for proper motions. For motions in the plane of the sky, yes, absolutely. And Gaia is already releasing some of that data. Because what they do is they measure the position of the star on the sky. And I forget, it takes them a year or something to map out 4 pi, and then they come back and they do it again. And so something like once a year or every other year, you revisit the same stars.
And so how does that compare to how well we should do with pulsars?
It's not good enough. I forget what the numbers are. Gaia is good enough to apply the corrections, and I completely swept under the rug in the first half of the talk all of this proper motion stuff all matters for sun-like stars too. Like you're measuring the radial velocity, and so you need to correct for these projection effects. And so Gaia is good enough for that, but it's not good enough. And it basically doesn't, it only tells you very crudely what the radial velocity is. And it tells you slightly less crudely what the tangential velocity is, but not good enough for this.
It's incredibly tantalizing. I share your excitement. So, I mean, as someone, as an outsider, I ask, where could the story go wrong? And like, if it's a pulse, I mean, I just feel a pulsar is something that, you know, per the diagrams, spews out stuff every now and then. And could there be like spurious like fluctuations in the like rocket equation type forces as it's spewing up and there's recoil? Or?
There are neutron quakes. There are neutron star quakes.
I also looked at millisecond pulsars for a different thing, and in the thousands of hours of observations of millisecond pulsars, not the crab pulsars,
Yeah.
slow rotating pulsars, there was one glitch. So they are extremely
Yeah.
stable.
But they're all.
The delta F over F, the rotation frequency is like 10 to minus 14 or so, fractional. So they were, you know, before atomic clocks really took over, they were supposed to be
Sure.
the time standard candidate and the millisecond pulsars. Also, comment for you, did you look at their new pulsars that Fermi found that are not in that Australian catalog? The
What-
Gamma ray telescope that are
Right,
close
right,
by,
right. What I haven't.
have better radial, you know.
I should.
Sorry,
There-
I went through this like
No.
painful experience.
And it's the really hard part is the overlap between Gaia and between what we need are binary pulsars, which are these pulsars that have visible companions that Gaia has done astrometry for, and I have not gone to look. So I should. So it's a good idea.
There's some really close by ones that, I mean, maybe the Manchester catalog, this thing got updated since I went through it last time, which was,
I'll go look because it's a good idea.
check.
Thank you. Yeah.
Yeah, millisecond pulsars are amazing because they are extremely frequency stable and don't
The-
have these kind of glitches that young pulsars like the crab pulsar go through, which is great for this kind of thing, and it's terrible for me.
there more questions? Well, you held up to your promise of being done a little earlier. So yeah, thank all the speakers today.